Hi, it's Kate, and this is the first video for week 10 of Math 23B. Last week we were introduced to differential forms and learned how to integrate a one form over a parameterized domain, which was a curve. Now we're looking to integrate two forms over parameterized domains, and two forms need two vectors to act on. Well, where are we going to get those? We're going to get them from our parameterization, just like we did from the one form. So here we have a parameterization in terms of two parameters, s and t. Yes, two parameters are governing three different components, very similar to when you're parameterizing a surface in R3, for instance. And the recipe for calculating this integral is just a higher dimensional analog of what we did last week. We take that parameterization, we take its Jacobian, and the columns of the Jacobian matrix are going to be the two vectors that that two form acts on. So if we're trying to integrate a two form over a surface, what we do is we need to parameterize that surface using two parameters, and then have phi, our two form, act on every tiny two parallelogram that's on the face of that surface. And that parallelogram is spanned by these two vectors, the columns of the Jacobian, and so that's what we are feeding to our two form phi. So when we're saying, oh, I want to integrate phi over this surface that's parameterized by this parameterization gamma, what that means is that we're going to compute this integral in parameter space. U is the bounds in parameter space. We are going to have phi act on the parallelogram that's anchored at a particular point on the surface that we're looking at. The parallelogram itself is spanned by these two vectors, which are given by the columns of the Jacobian of the parameterization. And that's what phi, the two vectors that we are feeding to phi. And then we will integrate that with respect to the appropriate bounds in terms of our two parameters that describe our entire parameterized domain. An important thing to note is that if we reverse the order of the parameters, instead considered t first instead of s, the parameterized domain would still be the same set of points, but each parallelogram that we would evaluate this two form on would have its order of its spanning vectors reversed, and so the columns of the determinant will be swapped and the sign is going to change by the antisymmetry of the determinant. So the actual function phi that we end up integrating is going to be opposite in sign. Now, of course, when we made a change of variables in R2, we actually used the absolute value of the determinant. Changing the order of the parameters changed the sign of the Jacobian determinant, but the effect was negated by taking the absolute value. So when you were computing something like surface area using this, it really didn't matter what order you considered the parameters in. Now, of course, with phi, computing the actual two form on the two columns of the Jacobian, that order does matter. If you swap them, it will change the sign because we're not taking the absolute value of phi there. So that's a slight difference when you're dealing with integrating two forms, or k-forms, I should say, any differential form, as opposed to when we were simply just changing variables before. Now, orientation is an important issue to think about. If we think about a one-dimensional manifold being like a city street, we can orient that manifold by making the street a one-way street. We say, this is the direction that traffic travels on it. And there are two different ways of doing this. The orientation of the street specifies the direction of the single spanning vector for any anchored one parallelogram at any point on the street. And so even though you maybe have come up with a parameterization for the street, the way to check that your orientation is correct or that the street is one way in the direction that you have decided upon or are trying to describe is by taking the derivative of that parameterization, gamma prime, because that will give you the direction of the velocity vector for a car driving in the direction specified by the one-way sign. So that's like a nice metaphor, an analogy, we should say, that describes exactly what it means to orient a one-dimensional manifold, and then also, given a parameterization, how to check your orientation of that one-dimensional manifold. Usually in a problem, as you'll see later, you'll be told exactly what direction, or the problem will have a common sense orientation that you're trying to strive for in your parameterization. And the way to check your parameterization of that one-dimensional manifold is to take gamma prime of it and see that that direction vector is pointing in the correct direction. And orientation is very important. Here's another example of it. When we're drawing coordinate axes on the plane, we always make the x-axis point east and the y-axis point north, so that to rotate the x-axis into the y-axis, it requires a counterclockwise rotation. But if we switch that, it would require a clockwise rotation. And then even in R3, the direction of the third basis vector is specified by the cross product between the first two taken in order, basically governed by the right-hand rule, so to speak. But if we swapped x and y, the direction of the third basis vector EZ would be specified by the left-hand rule, right? The right-hand rule would have it point straight down instead of straight up in how we usually draw the coordinate plane. So these are some examples of standard types of orientation that we sort of take for granted. We don't think about them at all. They just sort of happen. But convention states this is how the coordinate plane is oriented. This is how three-dimensional space is oriented. But what if you're dealing with a manifold that you're trying to parameterize that doesn't have a standard orientation, or you're trying to determine a standard orientation for it? And that's what our focus will be for much of this week. When we generalize orientation in Rn, where it's not quite so obvious that we have a right-hand rule, or the notions of things like counterclockwise or clockwise or one-way streets no longer make sense given the context of the dimensional space that we're in, we need to introduce the concept of a direct basis. And every basis is either direct or indirect. Note that if we swap two vectors in a direct basis, it becomes an indirect basis. And if we swap two vectors in a basis that's considered indirect, that becomes a direct basis. If we reverse the direction of a single vector in a direct basis, it becomes an indirect basis. And if we reverse the direction of a single vector of an indirect basis, it becomes a direct basis. And if we use the columns of a matrix T, this is really the easier approach here. If we use the columns of a matrix T to choose a new basis in R2, so that our first basis vector is the first column of T and our second basis vector is our second column of T, then the new basis is direct if the determinant of T is positive, and it's indirect if the determinant of T is negative. We'll be doing several examples of determining which vectors are direct, which vectors are indirect in various dimensional spaces this week.